A very good morning to all of you. I welcome you all to this current video lecture. Now, from last couple of video lectures, we have started the syllabus of the physical chemistry for semester first, and in that, we already started the chapter number first called as the chemical kinetics. So, in the last video lecture, we discussed the different important basic points from this chapter chemical kinetics. Now, after studying these basic points today, we are going to take one important point from this chapter, and the point is called as third order reaction. And within the same point, we have to study integrated rate law for third order reaction with equal initial concentration. So these 2 points we have to complete in the today's video lecture. Now before that, we have to look towards what is meant by this third order reaction. Now in the last video lecture, which we already discussed, that what is meant by the order of any chemical reaction. Now among that, this third order reaction is included in the this TYBSc syllabus. Now before looking towards the next point of this equation, we must know what is meant by this third order reaction. Now what is meant by third order reaction? So it is a very simple. If in a chemical reaction there is a change in 3 concentration terms, if there is a change in 3 concentration term at a rate determining step of a chemical reaction, then that reaction is called as third order reaction. Means what? If suppose if we write a rate equation or rate law for a particular chemical reaction, and if we take a summation of the exponents for all the components involved in the rate equation, then that summation comes out to be equal to 3. Then that reaction is called as the third order reaction. So it is very clear that if a reaction is a third order, then in that chemical reaction, the 3 concentration term undergoes measurable change during the course of a reaction. So that reactions are called as the third order reaction. Now for this clarification of this reaction, we are going to take some simple general examples of a chemical reaction. So for this purpose, I take here general example. Suppose I take here 3 reactants as A plus B plus C. They react together to form a particular product. So these 3 reactants are involved in a general chemical reaction A plus B plus C to give the particular product. Now we are interested to write a rate of this particular reaction. That's why how to write this rate? This rate is equal to minus dA upon dt is equal to minus dB upon dt is equal to minus dC upon dt is equal to, now how to write this? Now this is a rate of particular chemical reaction, total equal to K3 into concentration of A into concentration of B into concentration of C. Now what is the meaning of this? Now this is a general chemical reaction. For the same chemical reaction, if we want to write a rate of a reaction, then that rate is equal to minus dA upon dt equal to minus dB upon dt equal to minus dC upon dt is equal to, now this K3 stands for a rate constant. This K3 is a rate constant. So is equal to rate constant multiplied by A concentration of A into concentration of B into concentration of C. So this A, B, C is nothing but the concentration of reactant capital A, capital B and capital C at a particular time small t. So this is a particular rate of a particular chemical reaction at a particular time small t. Now this is one of the possibility of one of the possible example for the third order reaction. Now we may take another general example for the same third order reaction, as you may write here thrice A it gives the product. Thrice A it gives the product. Now what is this? This is another possibility for a reaction whose order is equal to 3. So we may take here 3 moles of this reactant A, it gives the product. So now we are interested to write again a rate of a reaction for this particular chemical reaction. Now how to write this? So again this is a rate is equal to, this is a rate is equal to minus dA upon dt, minus dA upon dt is equal to rate constant, that is a K3, into concentration of A cube, into concentration of A cube. Now how to take this A cube? Because the 3 moles of reactant A is there. So in order to write the rate equation for this particular general chemical reaction, we have to take here K3 into concentration of A cube. So these are the two possible general chemical reactions whose order is equal to 3. Now both these reactions are there and their respective rate equations is there. So this is a general concept called as the third order reaction. So what is by third order reaction? So third order reaction is such a chemical reaction in which there is a measurable change in 3 different concentration terms can be takes place in a particular rate equation, or in other words, if we consider the rate equation or rate law for a particular chemical reaction, then if we take a summation of, if we take a summation of the powers of the concentration term involved in a rate equation comes out to be 3, then that equation is called as the third order reaction. Now in this case, if we take a summation of these powers, what is this? This is a 1 plus 1 plus 1 comes out to be 3. So this is a third order reaction. Same case is there for the second rate equation or rate law. The power is equal to 3. So we can say that again this is an example of a third order reaction. So this is a general concept that what is by the third order reaction. Now the next point, depending upon the same concept, is called as the integrated rate law for third order reaction with equal initial concentration. Now what is the meaning of this? We have to derive one simple equation or one rate law for which, for a third order reaction with equal initial concentration of reactant. So if we take the equal initial concentration of reactant, so for this purpose or under which, what is the general rate law for a particular reaction, that we have to derive now. Now for the derivation of this particular equation, we have to consider a general chemical reaction. So again I consider the same general chemical equation as thrice A due to the product. Again I consider here the same general reaction. For this derivation, I consider the same general example that we already discussed here. So I take here general chemical reaction as thrice A, 3 moles of A, it gives the product. It gives the product. Now for the same chemical reaction, we already write here the rate law. So rate is equal to minus dA upon dt is equal to K3 into concentration of A, that is a cube. So this is a particular rate equation for a given general chemical reaction. Now nextly, we have to derive one equation or one rate law that is called as the integrated rate law for a particular third order reaction, that is a thrice A gives the product P. Now for this purpose, we have to consider here some basic consideration for derivation of the particular equation. Now this is a rate equation, so we may write this rate equation as, this is a minus dA upon dt is equal to K3 into concentration of A cube. Now this is the same rate equation. Now if I rearrange the given equation, you will get minus dA upon, I can take here concentration of A cube total equal to K3 into dt. This is a next simple step. Just I rearrange the given chemical, so given equation, simply I rearrange it. Now after this, what we have to take here? We have to just carry out the integration. We have to just carry out the integration. So for this purpose, we have to take some limits. Now we have to carry out the integration of this equation between the limits. We have to take here limit between t equal to 0 and t equal to small t, and sorry, t equal to 0 to t equal to small t, and concentration of A equal to concentration of A0 is equal to the concentration of A is equal to concentration of A0 and sorry to concentration of A to concentration of this capital A. So this is a simple limits in which we have to carry out the integration of the above equation. Now after carrying out this type of integration between these limits, time t equal to 0 to time t equal to t and initial concentration to the concentration A0 and concentration of A is equal to this concentration of capital A. Now if we carry out this type of integration, what you will get? So you will get here minus, this is a concentration of A0 to this concentration of A, then you will get here dA upon concentration of A cube. Now this equal to, the next is there K3 integration over t equal to 0 to t equal to small t into dt. So this is the next first simple step after this integration, minus integration over concentration of A0 to concentration of A, dA upon A cube is equal to K3 into integration over 0 to t into dt. Now in the next step, you may write here 1 by 2 is a 1 by 2, it is a 1 upon concentration of A square between these limits, that is a A0 to concentration of A is equal to, it is a 1 by 2, 1 upon concentration of A square, integration from concentration of A0 to concentration of A is equal to, next is there K3. So again this K3 we have to write here is equal to K3 into, this is a small t for time. So this is the next step after the solving of this integration step. Now next to this we have to write the next step for this particular derivation. Now you may write the same equation in the next step as it is a 1 by 2, it is a 1 by 2 into 1 upon A square minus 1 upon A0 square is equal to K3 into T. We can split up this term and we may write here 1 by 2 into 1 upon A square minus 1 upon A0 square. So this is the next step. Now if we rearrange the same equation in order to get a rate constant, then what is it? This is a K3 is equal to, it is a K3 is equal to 1 upon 2 into T in the bracket, it is a 1 upon A square minus 1 upon concentration of A0 square. It is a K3 is equal to 1 upon 2 into T into bracket 1 upon A square minus 1 upon A0 square. Now this is a equation for rate constant for a third order reaction involving two different concentration. One is called as a concentration of A and second is called as a concentration of A0 at a particular time small t. But now we are interested to derive one simple form of this particular rate equation for third order. We are interested to derive one simple form of this rate equation for third order reaction. For this purpose, what you have to take? We have to consider some parameters. So for the conversion of this equation into simple form, we have to consider these three parameters. So let we have to consider three parameters. The first parameter is a This first parameter is a small a. Now what is by this small a? Small a stands for initial concentration of reactant. This is the initial concentration of reactant. This is the initial concentration of reactant, that is a small a. Next is there, this small x is there, small x. Now what is by this small x? X stands for concentration of product. This is a concentration of product is there. Concentration of product. This is a second consideration. And the third consideration is that let this a minus x, this a minus x is there. Now what is by this a minus x? So a minus x stands for concentration of, this is a concentration of unreacted reactant, concentration of unreacted reactant at time small t, at time small t. So these are the three consideration we have to take into consideration for conversion of this equation into the simple forms. What are that three different consideration? This A is there. A considered to be initial concentration of reactant. This X is there, small x. What is by small x? X stands for the concentration of a product at a particular time, small t. And last is a minus x. Now what is by a minus x? A minus x is nothing but the concentration of unreacted reactant at a time, small t. Now by using these three different consideration, we have to consider this equation into the simple form. Now what you have to take here? Now suppose this is equation number first. This is equation number first. Now if I consider these three parameters, for these three parameters, if I take the two different concentration term, so what is it? Now in this case, two concentration term is there, capital A and A0 is there. Now for this concentration A 0, for this concentration capital A 0, what you have to take here is equal to small a, and capital A 0 is equal to small a, and this concentration of capital A is equal to A minus x. This is a minus x. Why this is so? Because we know that this A is nothing but the initial concentration. For the same term in this equation, what concentration term is used? That is nothing but the A0. That's why I take here, instead of concentration of A0, we may take here small a, and instead of taking this capital concentration of capital A, you may take here A minus x. Now what is our next function? We have to just substitute these values in a equation number first. Just we have to substitute these values in a equation number first. What you will get? We get the next step. After substituting these values, you will get the next equation as, we have to just substitute these values in equation number first. What you will get? This is a K3 is equal to, this is a K3 is equal to 1 upon 2 into small t in the bracket. We have to write here, now instead of 1 upon a, we have to write here 1 upon a minus x. So it will give 1 upon a minus x, this is a square is there, 1 minus x square, minus it is a 1 upon a0. Instead of a0 we have to take here a, so it will become 1 upon a square. So this is the next form of the equation by substituting these values in equation number first. Now in the next step, we have to just solve this equation in order to get the simplified form for equation number first. So for this purpose, if I solve this simple equation, you will get here K3 is equal to 1 upon 2 into t in a bracket. What you will get here, this is a square minus a minus x square divided by, this is a square into a minus x square. This is a simple form of the next step. If I just take here cross multiplication, so it becomes a square minus a minus x square divided by this a square into a minus x square. Now if we solve the given bracket, what you will get here, this is a K3 is equal to, this is a K3 is equal to 1 upon 2 into t in the bracket, it will be u a square minus, in a bracket it is a square minus 2ax plus x square total divided by, this is a square minus a minus x square. Now this is the next step after solving this bracket a minus x square. Now in the next step, just I simplify it. So again it is a K3 is equal to 1 upon 2 into t in a bracket, you will get here a square minus a square. This minus minus becomes plus, so it is a plus 2ax. This minus plus becomes minus, so it is a minus x square divided by, this is a square into a minus x square. This is the next step. What we can do here, just we multiply this bracket by this minus sign, so it becomes a square minus a square plus 2ax minus x square. Now we have to just cancel the opposite sign terms, so this a square get cancelled, and what you have to get here, this k3 is equal to 1 upon, I take this a square out of this bracket, this a square out of the bracket, so you will get here this 1 upon 2 a square into small t in a bracket, to a square into small t in a bracket. What you will get here, this is a 2ax minus this x square divided by, this is a just here now a minus x square. This is the remaining term. So what we can do here, just I make this a square out of the bracket, so it becomes 1 upon 2 a square into t in a bracket 2ax minus x square divided by a minus x square, and at the last we have to write the final equation of this third order reaction as, I write here final equation of this k3. So this at the last it becomes k3 is equal to 1 upon 2a square into t, 2a square into t in a bracket. What we have to write? Now I just make a common terms. This x is a common, so I take it outside the box. So it is a x in a bracket 2a minus x divided by a minus x square. What you will get here? K3 is equal to 1 upon 2a square into t. Now this x is a common, so I take here outside the this bracket, that's why it becomes x become common. So this is x in a bracket 2a minus x divided by a minus x square, and this is nothing but the final simplified form for third order reaction with equal initial concentration of reactant. So this is a very simple equation in order to calculate the rate constant for a particular third order reaction at a particular small time t. And in this simplified form, we have to take into consideration some simple parameters of a chemical equation, so a chemical reaction. What is that? This K3 stands for rate constant for a particular chemical reaction. This A is nothing but the initial concentration of the reactant. This A minus X is there. What is this A minus X? This is called as the concentration of unreacted reactant at a particular time small t. This t is a time parameter. This x is there. What is by this x? X is nothing but the concentration of a product at a particular time small t. So this is a very important equation as far as the solution of the numericals is concerned. For solving the numericals, we have to take into consideration this particular simplified form for a third order reaction. So today we studied the two simple concepts and important concepts from a chapter chemical kinetics. First concept is what is meant by the third order reaction, and related to that we derive one rate equation that is called as the integrated rate law for third order reaction with equal initial concentration. For this purpose, I take into consideration such a chemical reaction in which the 3 moles of A we have to take, it gives a particular product, and by using that particular general chemical reaction we derive first one equation for rate constant, that is a K3. We derive one equation, this equation. Now this equation is called as a rate constant equation for third order reaction. Now this equation can be simplified into the one simplified form of equation. For this purpose, I take into consideration these 3 parameters A, X and A minus X. By using these 3 different parameters, at the last we derive this particular simplified form of a rate equation for third order reaction. So with this, we have to conclude today's video lecture. The remaining points we will cover in an upcoming video lecture. So with this, I stop here. Thank you.